Okay, last time we looked at this, structure of neural network. We said that we can use neural networks for natural language processing. In this simple example, we were trying to do the NER, named entity recognition. We were trying to make a decision about this Paris. Is this a location, or is this a name, or is this an organization, etc. So we feed these vectors of a museum in Paris are an amazing to the first layer of this network, and the output is obtained by multiplying the input vector with a matrix, and that's going to give me another vector, and I will add that with the bias vector, and I will pass it through this function, which is a non-linear function. Okay, it could be a sigmoid or something else. Most of the time it's going to be a sigmoid like this. Then I will get another vector, and I will multiply that vector with our new weights, another matrix, and that's going to produce me just two-dimensional result, and I am going to run my softmax on it to say that Paris is either a location or not location. Okay, so somebody asking a question? No. Okay, good. So that's what we were doing last time, and we said that if the weights, okay, how many parameters do I have in this case? I have these matrix parameters, biases, and these are the parameters. If I can figure out these parameters, and I expect this network to work up to some performance, and the important thing here is that finding these parameters, and for that one we have introduced the backpropagation. We said that any function can be optimized with respect to those parameters using the gradient descent. What is gradient descent? It is like this. Okay, if I have a function like this, x plus 2 square. Okay, so find the optimal or the minimum position for this function. How am I going to find it? Of course, this is a closed form formula. It is very easy to take the derivative and equate to 0 and solve it. Yeah, but I like to find it in a way that I can use a numerical solution so that it can be generalized to thousands, sometimes millions of parameters. I have just a single parameter. So what am I going to do? How do I draw the, so where is the, if this is minus 2, yeah, it will be something like that, right? 0 to, yeah. So this is minus 2, and I guess this is 2. No, this is 4, right? 4. So if I started from any point, like let's say I start from minus 5, I will take the derivative of it, and the derivative says that I am decreasing this way towards the right. So this one, my slope is positive, so I should go towards right. And if I keep moving towards the derivatives direction, okay, opposite of the direction, I should hit this point as the minimum. In fact, yeah, I was doing this before the class. Yeah, okay, yeah. So let's do this. This is my function, right? Okay, my function is fx, and my function is how am I gonna make this bigger? Can you guys see it? Do you guys see this? So this is, okay, this is a to my x. This is fx. So let me make this like this. This is fx. This is a2 plus 2 times a2 plus 2. So this is a2 x plus 2 squared, right? If I take the derivative of, okay, if this is fx, f prime x becomes what? 2x plus
2x plus 4.
2x plus 4, right? So that would be my derivative of it. So I put it in there already. Okay. So it is this one. 2a2 plus 4. a2 is my x, right? And then this is my gradient descent equation. It says x minus, okay, this is old parameter, minus some learning rate times gradient of the my function itself. So it's going to be x is a2 is my x, okay, and minus e2 is my learning rate here, times c2 is my derivative, okay. So if I started from minus 3, I put it in there, it says that now your x has to be minus 2.8. So I get this minus 2.8, I put it in here, okay, and I calculated this, and now I became minus 2.64, and then minus 2.512, and it goes until I started at 43 iterations, but if I like, I can move this like maybe 200 iterations. As you see, after some time it converges to minus 2 very nicely. Yeah, after some, like, maybe I can make this a little bit bigger. Yeah, okay. So up to the maybe 10th digit after 100 iterations, it is done. So it looks like if I can take the derivative of a function, I can optimize it that way. I can find its minimum point. Okay, that's what we are doing with this equation, and this is the learning rate, by the way. I can play with it. Let's play with it. Let's start it from, let's say, 100 minus 100. Okay, so it say that I am dropped to 80, then 64, then 53. Okay, it goes that way, and after some iterations, okay, as you see, after 100 iterations, again I have converged after some more iterations like that. So after 118 iterations, I converge to minus 2, which is the optimal point for that one. If I play with this number 0.1, which is the learning rate, let's make it a little bit smaller, 0.01. So what's your guess?
Go to 200 iterations.
Will increase, I guess.
Yeah, it's going to be much slower, right? So it is going slow, very slow. It is going slowly but surely, drops down to some nice numbers, but 200 iterations were not enough. It is very, very slow, very slow. How about this one? If I make it 1, very, very, very large step size or learning rate.
Will it converge?
I am asking to you, I am the teacher.
I think it will be bouncing around.
So, yeah, it is doing this, minus 100. So, it is going all the way to the other side, then it's coming back again. It is oscillating between these 2 points, and it is not doing anything useful for me. So, step size large is bad, step size small is not that efficient. So, you need to find something like this, 0.1 or 5. How about 5? Is it? No. Oh, it is by pure coincidence. I perfectly find it. By pure coincidence, yeah. That, I mean, if I started from 120, what's going on?
I think it's 0. Should it be 0 point, not?
No, it is correct. It's not point, it's a comma. Otherwise this would have been, how come this is 4? Why is it just locking in? 0.1. 0.5 is the perfect step for this function. I found something. What's going on?
Which count?
Yeah, it just whatever you do, it just goes in there. But this is a very, what do you mean? This is a very concave function, convex function. Sorry. So you are going to find it anyway because I mean, this is the graph, right? I mean, wherever you start, you have to end up in the smallest number. But if I have functions like that,
Local minimum is also global minimum.
yeah, okay, it has one local minimum and one global minimum. They coincide each other. But if I have something like that, I would be in trouble. There is no perfect learning rate for that one. So, but this is what we are doing actually. I just put it in there, and you can do. I mean, I could have said that. Okay, f x y. I could have said x plus 2 squared plus y minus 2 squared, right? So this is a function of two variables now. When I take the derivative of it, I don't have a single scalar derivative anymore. I have two derivative of, I have a vector of derivatives. A vector, a derivative with respect to x and a derivative with respect to y. So I have to keep adding this vector to my old vector, to my xy. So I can now optimize any kind of function that I have as long as somebody is giving me this kind of a formula. Well, and I am lucky because I have all these formulas, okay? I have this matrix multiplications, additions, and this f is a sigmoid. I can take the derivative of it. In fact, I am lucky because taking the derivative of the exponential function is very easy. It is the same thing, right? So this is the whole story of gradient descent. People have discovered this. Of course, they did not discover the gradient descent in 1980, but they discovered that if I use the chain rule plus the gradient descent, okay, because I am taking the derivative of loss with respect to these parameters and with respect to these parameters and these parameters, okay, and they are at this different levels, so I have to use the chain rule. That's the back propagation. With the use of the back propagation, I can get some good enough values for my optimal function. That's what we did last time. Okay, that's what we did last time, and we looked at it. Okay, I showed you this example only, but if I have more than one variable in my function, I can do that. But if I have a function of functions, okay, so this means that at every layer I have many nodes. So this is one function, another function, another function. So in my case, I think we had 8 nodes in the first layer, and my derivative would become a Jacobian matrix. Instead of a vector, it's a Jacobian matrix. And the mathematics is well defined, and I can follow these, and with a simple Excel sheet like that, I can solve it any way I like. But this one, okay. So it's a little bit better. So this kind of converged after 50 iterations. So this learning rate is very important. With the learning rate, with the learning rate, you can. I mean, it's a trade-off between how fast you are going to converge or you are going to bounce around or not. Okay, and it is not easy to choose learning rate all the time. And most of the time, we don't choose learning rate like a constant. It is adaptive. It changes during the optimization. It becomes a little bit different. By the way, I have a single parameter in my system. Our normal neural networks have hundreds of parameters, thousands of parameters. For each parameter, it makes sense to choose a different learning rate. Okay, that's called adaptive learning rate, and that's called learning rate individualized for each parameter differently because each one is behaving differently. Okay, let's go back to our slides, and we talked about this with the back propagation. So most of the deep learning or neural network libraries that you are going to use, they support these that back propagation already. And if you come up with your own way of adding new nodes to your network, all you are going to do is that, okay, for example, this one, I get two inputs and one output. So my output is this, x times y. This is for the forward case. For the backward propagation, this is how I calculate my dx and dy. So just multiply dz by y and multiply dz by x, and that's it. Okay, so that was it. By the way, you don't have to calculate your derivatives using the mathematical formulas. It is always possible to calculate your derivatives numerically, and this is the easiest way to calculate the derivative of a function. All you do is just add a little bit number to the function at x, subtract, then divide it by 2h, and that's going to give you an approximation of the derivative if your functions are numerically defined but not defined in a closed form. Okay, but usually we don't do that because in deep learning we have all of our functions nicely defined.
Yeah, this is the definition if its limit going to 0, right? For the derivative.
Well, yeah, I mean, this h has to, I mean, the formal definition of it, h needs to be very, very, very small. It goes to the limit of 0. But on computers, we don't have such a thing. We have small numbers like this. Okay, we have small numbers like that. Again, we have the underflow and overflow problems with our computers, and I mean the world of numerical calculations is very different than the theoretical world of mathematics, because in theoretical world of mathematics there are infinitely many real numbers. On computers we don't have infinitely many real numbers. The number of real numbers is limited, okay, because of our precision limitations. We may have very, very large number of real numbers, but they are limited. Okay, so that was it. So I mean, this is good, but I mean, this is good, but at the end, we didn't do much in terms of doing natural language processing. So today we are going to do it more realistically. Okay, a little bit more information about these optimization stuff. Up to now, we have looked at this much. Our loss function is like this, okay? Everybody at the end of it, everybody should satisfy the ground truth. Okay, remember this one, the logistic regression, or sorry, the softmax function. Each label should be predicted correctly, and this will be my loss, negative log likelihood. But usually, for very large number of parameters of theta, this doesn't work very well. We like to regularize our parameters like that. Okay? Just read this equation. What does that say? Okay, minimize this part. Minimizing this part means that be compatible with the already labeled data. How about this part? What does it say? It says
lambda times the sum of all the parameters squared.
So just read me the English. Don't read the formula. What is the meaning of it? We minimize this whole thing, right? We minimize it. This part will be minimized, and this part will be minimized. What does it say?
It
says
parameter as possible.
All the thetas should be as small as possible. Right? If I make all the thetas 0, this part would be very, very happy, right?
Okay.
But this part wouldn't be that happy.
Okay.
So there is a trade-off between them depending on this lambda. Okay. So this one says that achieve both of them. Keep your parameters small, all those weights, W's and B's and U's. keep them small. At the same time, your labels are important too. So it's a weighted optimization problem now.
Why do we want to keep them small?
That's called regularization. Without this regularization, we have the real risk of overfitting our training data. We learn such parameters that our loss function is really minimum for our training data, but when the new data comes in, we perform very poorly because we memorize our training data. Okay? Doing this, we are saying that we are regularizing our parameter space. We are giving it a more order. Okay? We are saying that you should be around 0. Around 0 is a constraint. If you do that, it turns out that this is a much better generalizable parameter finding problem for our networks. Our search space is very large for this theta. If you, the example that I showed you is just one dimensional, and I think I talked about two dimensional stuff too. We are talking about 1,000 dimensional space here, and each dimension is a real value again. Okay, it's 1,000 dimensional space, and there are infinitely many positions to satisfy the minimum position for this one. Okay, so space is so large, space is so big. Without doing this kind of a regularization components, without adding these kind of regularization components to our loss function, we end up most of the time memorizing our training data. It doesn't generalize. For the new data, it just doesn't generalize. So this regularization, this kind of I'm not saying that this is the only type of regularization technique. This kind of regularization techniques produces better results. Okay, these kind of optimizations are also called ill-posed optimization techniques. Okay, why ill-posed? Because there are infinitely many solutions to our problem, and any of them will minimize or almost minimize this loss function. But I need to select the best ones out of them that will generalize. So this is a way of achieving that one. We don't have a very convincing proof for this one, but the experience shows us that if you do that, keep your number small around 0, that's going to work better. Okay, and this graph is very important. Okay, if I keep, remember my Excel document, if I keep going further and further, at the end I am going to find a minimal point. I know that gradient descent tells you that. But usually, if you keep going this, okay, further and further, more iteration, I spend days and weeks on it, and I get a very small training error. But if I test the final system on the new data, my test error would be very high. Okay, that's called overfitting. I overfit to my data. So the nice thing is that don't overdo it. Just cut it somewhere here. Okay.
And how to know where to cut it?
Well, that's a very good question. If you can find the answer to that one, I will give you 2 Nobel Prizes. One for figuring that out. The second one is getting so rich in so small amount of time. We don't know. Okay, we don't know. I mean, in real life, in the laboratory, okay, I can do this testing. I can determine that point. But in real life, I don't have the test data. I don't know which one is better. Okay, so usually, how do you understand that you are overfitting your training data? If your loss is 0, okay, then you are overfitting it. There is no way that you can get a loss of 0 or very, very close to 0 in the real data, because in the real data there is noise. Okay, if you get 0, that means that your data is too easy. You are memorizing everything in your data set. It's not going to generalize. It should be a little bit higher than 0. But how do you know that you are at this point or this point or that point? Obviously, this point is the best one.
So we are striving for a point that the loss is low, but not too low.
Yeah, that's kind of confusing. Yes. Well, that's what people have been doing. And some people does this. Okay, they iterate over their data, more epochs. Okay, and after that they see that it is becoming so low. Okay, they come back and they say that, okay, I'm going to use this point. Okay. So that's something. Okay, so this kind of regularization technique just closes this gap of overfitting. Okay, because this one says that I'm going to force it even more. I'm going to give you a few more regularization techniques, and these are completely counterintuitive, but they work. Okay, so this is a regularization technique produces models that generalize well, and another one is dropout. In the dropout, we say that at the training time, okay, we randomly set 50% of the input to 0. Okay, for 50% of the neurons, we say that I don't get any input from the outside world, so they are blind. Okay, while we are training it. So you ignore whatever you have achieved at that point. Okay, for those neurons. Then I randomly of course, switch those 50% setting to 0 value through the training, so that I don't completely depend on my training set. So I am kind of introducing noise to my training set. Okay, if I do that, it turns out that it works very well for stochastic gradient descent. Okay.
50% isn't it too large?
What's that?
50% isn't too large.
Well, of course, I mean, no, actually, I mean, sometimes you would say, remember our neural network playground? There was a regularization technique of dropout, and I think you can adjust it. No, sometimes 50% is right, just enough. And this worked very well for certain kind of networks, but newer kind of networks, this doesn't work very well. I mean, nobody uses this dropout mechanism anymore. So that's why I say, I mean, we work very hard to achieve those numbers, and now we are forgetting some of them now, but what's going on? Yeah, for some networks, in order to prevent overtraining, memorization, we do these kind of desperate techniques. Okay, nowadays we don't use dropout anymore, especially for the ResNet, and we are going to see it in a few minutes. Nonlinearities. Up to now, we only talked about the sigmoid. Okay, without the nonlinearities, there is no point of using more than one layer of network. We talked about this. Everything collapses to a single one equation. With the nonlinearities now, we have what we call multi-layered learning. Okay, so this is one way of nonlinearities. This is another one, hyperbolic tangent. These two are very similar actually. You see, this is 1 over 1 plus e to the minus z, and this one is like just 2 times logistic regression to z. Okay, so these are relative. These know each other. This is from 0 to 1. This one is minus 1 to 1. And some people said that why don't we approximate this complicated equation or that one, because it requires some taking exponential numbers. How about this one? Minus 1 if x is less than minus 1, plus 1 is plus 1, and between them it is just a linear line, x. So these 3 pieces of linear functions put together. Okay, this is called hard hyperbolic tangent. Okay, so okay, of course the advantage of this one and this one over this one is
more accurate.
Not exactly. Well, I mean, we are not after the accuracy for this and this. There is non-linearity, and the nice thing is that whatever you give, it puts everything between 0 and 1 or minus 1 to 1. So this is what, but these two are differentiable, right? I can take the derivatives of these two functions, but there are discontinuities at these 2 points.
Right.
So numerically, it is difficult to take the derivative, but we take the derivative anyway, and it works very well. Okay. Okay. So these used to be the most popular nonlinear functions. Then somebody invented this. It's called ReLU, rectified linear unit. Okay. Remember, we multiply our input with the W matrix, then add the B vector on it. Then after that, we feed our results through this function. Less than 0, 0, greater than 0, just X. It's called ReLU. And this works much better than any of those.
Didn't we try to keep it between -1 and 1?
Yeah, we don't do that anymore. Well, I mean, this is good for the classification layer, because in the classification layer, you need to put everything between 0 and 1. If it is close to 0, that means false. Otherwise, it's 1. Yeah, that's true. But in the hidden layers, you don't have to do that. In the hidden layers, a non-linearity like that is good enough. Okay? And other variations of it, don't make this 0, but just a linear function with some slope other than 1. And later somebody came up with this solution. I don't know how effective this one is, but this is good enough. And I think when I showed you the playground, neural network playground,
Yeah, there was.
I think we were using this one. Or maybe we can go there and check that again. Where is it? Neural network playground.
It was TensorFlow.
Where is, okay. So this is hyperbolic tangent activation. I can make it to sigmoid, okay, or ReLU. ReLU works amazingly well. I mean, in this case, you are going to see just converged. What happens, question for you, what happens if I choose linear?
Much slower.
What?
Will it be slower?
It
Well,
won't,
it will be worse, it won't converge. Why? Because
It's not
our
probably
data
it's
is
more
not-
than one layer, the point of having more than one layer is adding non-linearities in it. If I have a linear activation function, that is as good as a no hidden layers neural network. It will not converge, it will not find anything. So, see, as you see, it is just drawing a line. Okay? It's just drawing a line, that's it. Whatever you do, it doesn't matter. Linear is bad if you have more than one layer, okay? You definitely need to add non-linearity, okay?
does it change all neurons activation function?
What?
Does that drop down changes all neurons activation function? All neurons are linear.
Well, I mean, if you change it, the
All neurons are
activation
sigmoids.
functions are here and there, they all will be sigmoid now,
Okay.
all of them. Let's make it this ReLU, and it's going to converge like that. By the way, just keep this in mind. Okay, let me take this screenshot of it. I took a screenshot like that. Okay, let me start from the beginning. Converge. It
30.
converged. Let's see how similar those two are. Are they similar?
Yeah.
Yeah, I think so. Someday, yeah, you know, it is not that similar, right? This part is a little bit different than that part. it is more sharp, I guess. So my point is, every time I start, since this is stochastic gradient descent, okay, every time I start, it initializes all those weights with random values, and since it is stochastic, it chooses different order of evaluating the training data.
What if we tried with tan h? Will it?
What?
If we tried tan h, hyperbolic tangent, will it converge?
Yeah, well, if you have the non-linearities, yeah, it should converge, but sometimes it's fast, sometimes not that fast. Let's see. See, it is more non-linear than the ReLU, and its shape is more rounded.
Yeah.
With the ReLU, it is more like
Okay.
jaggy, right? So it converged.
There are small number of neurons.
What?
Small number of neurons that exist.
Yeah, well, we can
Yeah,
do
because
much
the
further.
problem is like this.
But most difficult one is this one. It is having lots of difficulty for it. See, this one is training loss, and this one is test loss, and both of them are doing very bad. And this is not going very well, and the learning rate is this. Okay, let's try to do something. Trying to do something. Okay. Let's do some regularization. This is L1 regularization is just minimize the absolute value of those parameters. L2 regularization is minimize the square of those parameters. And let's see what's going to happen now. Usually harder the problem, more likely that your regularization is going to be, your regularization rate cannot be, okay. Regularize this much. Remember that lambda? It has to be non-zero, otherwise regularization has no effect, right? So it is much slower now. Tan h is, it looks like doesn't move much because the regularization is maybe too much. I'm not sure. Yeah, regularization is keeping us. Let's do that and make it faster with the ReLU. Okay. It is as good as random, 0.4. I am getting something. See the oscillations? There is some oscillations going on. It's going back and forth, back and forth. I don't know, maybe we wait, it's going to be okay. Let's go to slides and we'll come back to this and we'll see if it's going to be anything. Okay, for the parameter initialization, this is some of the techniques, okay. Normally you just initialize the weights. It's two small random numbers, okay. If you initialize all of your weights to 0, okay, if you initialize all your weights to 0, or if you initialize all of your weights to the same number, then your gradients will be 0. That's not going to be, so usually we choose them random numbers. There are other techniques too, uniform distribution from -r to +r. These are small numbers. And there is a Xavier initialization technique. This guy says that, okay, I am going to initialize my weights proportional, okay, it has to be from the normal distribution. The variance of that normal distribution will depend on these two numbers, okay. Those numbers are the fan in and fan out of the layer. What is fan in, fan out? The number of inputs and number of outputs from that layer. So if you have many inputs and outputs, these numbers will be large. and 2 over large number will be small, so my variance will be small. Otherwise, my variance will be large. That's, you might ask, I mean, how did you come up with this formula? Well, I mean, in deep learning world, people don't ask those kind of questions much. Okay? And when the best answer usually, if you ask that kind of a question, the best answer is, but if you ask them, why did you do that? Okay? The answer is usually,
It performs well.
yeah, it performs better. I don't know why it performs better. Okay. For the optimizers, plain stochastic gradient descent that I showed you works, but for large systems, for complicated systems, these are the type of gradient descent systems. Adaptive gradient descent, RMS prop, Adam, okay, sparse Adam. Okay, some of them again, they use sophisticated adaptive optimizers. So per parameter learning rate and etc. Or sometimes we do this. Our learning rate decreases over time. Okay? Do you know this formula? E to the minus kt. T is time. This is simulated annealing formula. It comes from the nature. This is the formula for calculating energy of a molecule while that molecule is frozen. So it has to lose all of its energy so that it can be frozen. And we know that it behaves optimal in some sense, and they get it from there. So they choose this learning rate exponentially. And I think it is available in our system too. This guy is still doing this. Is it stuck? Maybe. Do we have that learning rate? Do we have adaptive learning rate? No, we don't have adaptive learning rate. Yeah. I am going to let this run with a crazy number. Crazy number like this. Okay. It might work. Too crazy? Less crazy maybe. Because it's kind of stuck in a local minimum or something like that. Okay, so those are the learning rate. Okay, so let's come back to natural language processing with the neural networks. Okay, remember our original problem of language modeling? We know this, right? Given these words, the students open their blank. So what would be the best word to put in after these 1, 2, 3, 4 words? The students open their books, their laptops, their exams, their minds. All of them seems likely, but which one has the better possibility? So if we can calculate this, then that means that we have a language model for English. Okay, and we already calculated this one with the n-grams, right? We have this n-gram-based language modeling, and it worked nicely up to some degree. Of course, Turkish had problems. Why? Because with the Turkish, we have lots of morphological possibilities for each word, and when you say the öğrenciler kitaplarını açtı, kitabı açtı, kitaplarıymış gibi açtı, etc. So lots of words that you can put in with the root word kitap, and then lots of suffixes at the end. So morphology and n-grams are not very compatible for languages like Turkish, but anyway, it works up to some degree, some performance degree, some performance level. It works good for the English, okay? And in fact, up until 2015's n-grams were much better than all the other things combined. So we didn't give up. So we know this, okay? We can guess this word, or given a sentence, I can assign a probability to it using the chain rule again. Okay, you remember this? Given a sentence, I can assign a probability to it We learned that too using the statistical language modeling. It's a very useful tool too. I mean, we have been using this all the time. When somebody says, "I'll meet you at the," our cell phone editor immediately puts airport in here or something else. So it is using some kind of a language model. Or Google, when you say what is, then just the language model say that I'm going to put this one. Of course, this language model depends on where you live and depends on your history and etc. But it's a language model, and I just used this language model a few minutes ago with the Google. Okay, so we can do this using n-grams, using 4-grams, trigrams, bigrams, and etc. I am not going to talk much about them. And our basic, remember our basic assumption about the n-grams were this, okay? A word depends only on the words previous, that comes previously. And this one depends on the 3 words, so this one is using the 4-gram model. So it ignores the other previously occurring words that we just discarded. So that's a very big shortcoming. Why? Because I need to remember stuff from the way back from the sentence. That's one problem. The others are collecting statistics for these kind of cases is difficult. Okay, because student opened their occurred 1,000 times maybe. With the book, it occurred 400 times. With the exams, it occurred 0.1 times. Okay, but for the other words, they will occur almost the same amount of time. Most of the time, it is 0. Those are the problems. So remember smoothing. Okay. Students opened their W and W never occurred. So that probability is 0. We said no. We use smoothing. That's one thing. Okay. That's not one thing. So we have to apply smoothing. That's one partial solution. The other solution could be back off and etc. We looked at that. We looked at these problems too. Okay. And storage is maybe the biggest problem. Storing 4 grams for English is gigabytes of space. Storing 5 grams for English is terabytes of thing. And accessing them, keeping them sorted and etc. is a problem. So storage problem with n-grams is a very difficult thing. And we don't like 5 grams because they are not sufficient enough, precise enough for our work. And yet we cannot find other stuff. The other problem is with the n-grams is sparsity problem. You see, today the company, today the bank, they have the same probability. Then after that, I have Price, Italian, and Emirate. Okay, so I mean, there is like 2 times difference between these two, but I cannot differentiate between company and bank. Why? Because I mean the number of occurrences is so small. 1 plus 1 minus makes lots of difference. So this is called the sparsity problem. Not much granularity in the probability distribution. Okay, not much probability. I mean the order is correct, but I cannot differentiate between these two in this case because of the sparsity problem. Okay, so these are some of the problems with the n-grams. Of course, we use the n-grams to produce text. Okay, we produce text and we talked about this. I think this one produced using 4 grams or 5 grams. Today the price of gold per ton, while production of shoe lost and shoe industry, the bank intervened just after it considered. But grammatically it is kind of correct, but it is incoherent, it doesn't make any sense. We are expecting it because it doesn't remember words from the beginning of the sentence, just keeps doing okay grammatically correct things, producing grammatically correct things over and over and again. Doesn't read very coherent, but grammatically kind of okay. So we are going to come back to our neural networks, and instead of building a statistical language model. Now we are going to produce a neural language model. Okay, that's what we are trying to do. And we are going to solve many of those problems, such as the sparsity, such as the storage problem, and later such as the remembering words from the way before 4 words ago. Okay, so that's what we are going to do. But first, I need to take some break. Let's take 15 minutes of break. 30, okay, 14:40. Let's be here. 14:40. And I forget about your attendance when you come back. I will give you the attendance.
Makale sunumları haftaya mı olacak?
Efendim?
Makale sunumları.
Birinci onu da konuşuyorum. Haftaya yeni ders anlatacağım biraz ben. Belki onunla beraber yapacağız. Kaç kişi yapacağız?
Söylemeyecek bir şey final öncesine kadar genel olarak öyle. Sorabilirsiniz.
Savunma korkuyorum. İyi var.
Genel olarak demeyeceğim bir şey. Finalde beraber.
Tamamlaman gereken dersler var. Lisansa göre çok az zaten.
Aha.
İşte herden 2-3 ders düşüyor. Sonra tez gönderiyor. Tez yazıyorum işte bir konu üzerine.
Şu an belirledin mi bir şey?
Evet, literatüre yeni bir şeyler katmam var yani yapılmamış bir şey. Konumuz da belli zaten şey. Semi-supervised learning from multimodal remote sensing image. O kadar.
Buraya kamera çekiyor. Kamera çekiyor. Meşhur olmak.
Ben burada sıkıyorum ya. Kamera muhtemelen buraya alıyor da şuraya almıyor.
Nasılsın? Hazır mısın quiz'e?
Ne?
Quiz'e hazır mısın?
Yok hiç yani. Derslere tam bakamadım ya.
Ne quiz'i?
Organizasyon.
Kaçta?
Yarın öğlen.
Ha. Hoca quiz mi yapıyor böyle?
Uzun oluyor ya. İşte uzun oluyor.
Sınavlardan önce yapıyor.
Doğru yapıyordu ya ben de hatırladım.
Sağ olsun.
Ders İngilizce mi anlatıyor Alparslan?
Evet ya. Arada
Alparslan Hoca da mesela sevmez Türkçe İngilizce anlatmayı ama
hangi
Türkçe çok daha iyi anlatıyor. Ama
Arada unutuyor böyle. Türkçe geçiyor. 1-2 saat Türkçe unutuyor. Yani unutmaya da oluyor. Olabilir bilmiyorum. Bilerek de yapıyorum. Arada anlatıyor.
Yola gelsene ya orada nasıl görüyor musun? So previously we did this for name entity recognition. For the center word, we are going to say it's a location or not location. That's what we did. This is of course much different than language modeling. With the language modeling, we need to output this probability given the first key words in a sentence. Give me the probability of the next word if the next word is this one. Okay, so like the Ngram models, we are going to do this. If you give me these 4 words, I'm going to guess the probability of any word given after that. So that will be it. Okay, this is very similar to name entity recognition stuff, but at the end I am guessing the probability of the word that may come from after this word there. The students open there. So remember, this is softmax. Okay, softmax of all possible words that can come, and the words that have a higher probability will have larger values in there, but none of them will be greater than 1.0. And I have this hidden layer. Here. This is my inputs, and that's basically the same structure, but I am using this network. Thank you. I am using this network. I have 11 people registered, only 5 of them is signing. Okay, so Again, our task is the same. Thank you. Our task is the same. Figuring out these parameters W and U for this network, and after we figure this out, this becomes our language model. Doing exactly the same thing, as before, guessing the probability of a sentence or the probability of the next word, but this time instead of using the engrams, we are using a neural network like that. Okay, and we solved a number of problems. Okay, no sparsity problem. What do I mean by no sparsity problem? Remember, we didn't have any gaps between different words. Some of the words have the same probability. We don't have that one. And nice thing is, we don't need to store all observed engrams. This is a very important advantage because we are feeding our vector representation of the words and multiplying with this matrix and this matrix, and this will give me the outputs. Maybe I can add more layers, more number of nodes in the layers, but that's it. Okay, so those are the problems that we have solved so much. So this guy Bengio, they proposed this solution as a neural language model. During those days, they were very, very bad compared to engrams, but later they came up with better ways of doing this. Nowadays, these kind of networks are the best. Okay, one of the problems is this one: fixed window is too small. Okay, this one is too small. 4 words, then after 4 words, guess the next word. Okay, well, nothing prevents us from expanding this window, right? Let's make this a window of size 10. Well, previously it wasn't possible because anything larger than 5 grams, even Google cannot do that. Okay, even Google cannot have the data trained on, and even if you have the data, the memory requirements are so large. So, well, in this case, I can open up my window up to 10, 15, 20 words, but usually even the 20 words are not good enough for me. Okay, are not good enough for me. Why? Because sometimes it is important to have. Let me show you one example. Where is my example? Okay. Wow, it's too far. But since I started doing this, where did it go? Come on. I think it was in the. Go back. No, I think it was in the other slide set. Okay.
May I ask a question?
Sure.
So we give the neural network a window of size n, and the neural network gives us a one-hot vector of all the words that we have in the dictionary.
Yeah, it assigns a probability for each of the words, okay, that you have in your dictionary.
Okay.
That's the idea. Okay, I'm going to give you this example. Maybe I can print it. There was a, yeah, okay. So let's look at this sentence. When she tried to print her tickets, she found that the printer was out of paper, toner. She went to the stationery store to buy some more toner. It was very overpriced. After installing the toner into the printer, she finally printed her what? Tickets. But you have to remember tickets from all the way back. How many words from the back? 1, 2, 3, 4 lines, 40 words back, right? Okay. So that's a very, very large window, and can you say that 40 word wide window is good enough? I can't, because sometimes to guess the word you need to go back to the beginning of the chapter sometimes, right? Sometimes you need this. So fixed window size is not good enough. we need to come up with something better. Okay, fixed window is too small. I need to come up with something together. And other one is okay, windows cannot be large enough. The other one is that the weights for the x1 and weights for the x4 are kind of different. Okay, I don't want to do that. I don't want to treat the first word and the last word differently. Well, that's true, but I don't want to keep using different weights for the 5 words before than 3 words before kind of thing. So we need a neural net architecture that can process any length input. And luckily, even before these guys, those kind of networks were available. They are called recurrent neural networks. The idea is take only one input to your network. Okay, take just one input, just one word, and you can output whatever you want. After this word, use your internal state as a side input to your network again, and use your second word. So your network, this is the same network as this one, gets the input from the current word, also the previous internal state of your network of the previous run. So your current input and the internal state of your previous run. After this runs, your current input and your previous internal state. So put them together and you output something. So I keep using the same network over and over again. While I am running this on this network, I observe the current word. I also remember whatever happened in the previous state, and this one remembers that one, this one remembers that one. So in theory, this goes all the way back to the first word of the sequence, and I don't have to choose a fixed window width. My window width is just one. That's one word, and you cannot do any better than that. It is just one, but this has the potential of remembering as far as the beginning of the whole sentence or the paragraph or the document.
So here we have only one network with 4 nodes. That's it.
Just one network, yeah. Just a network is able to take in the current word, also taking the internal state of the previous run of the same network.
And how do we initialize those networks? So the
Zero.
network takes 0. Okay.
Yeah, just 0 or just random small numbers. Okay. Sometimes it's called conditioning actually. Sometimes you know what they do. Sometimes they give as the initial value. Okay, they give a picture. It's 2-dimensional picture. Okay, and this network starts talking about that picture. It just captions it, gives a caption to it. Okay, and sometimes you give a sound file, the speech, and this one acts like a speech recognizer. Okay, so those kind of things are possible, but those are out of scope of this course. Okay, so these are called recurrent neural network because you keep using the same network over and over again, and that's the core idea. Apply the same weights W repeatedly. Okay, and it looks like we solved this problem of length. Any length is now possible. Also, we solved the problem of no symmetry in how the inputs are processed, because whatever the input is, I am applying the same network. So I am not treating the first word and the fourth word differently. I am using the same network over and over again. That doesn't mean that my network is a very small one. It could be a large, but at least it is going to be symmetric. Yes?
You said we don't want to use different weights for each vector, each word.
Yeah.
Why don't we want? I couldn't understand.
But the problem here is this: why should I differentiate the word before me and the fourth word before me and third word, etc.? So they are just words. Of course, the sequence is important, But just because a word comes like 3 words before me doesn't mean that I should use a different weight for them. Okay? Wording is important, sequence is important. I should remember the sequence, but using a different weight for the one before for me, the one that is for before me is not a good idea. Okay, so we solved these both of them at the same time, and this is what we do. Okay, these are the at the beginning for each word I had the one-hot encoding. Okay, I multiply that one-hot encoding with remember our matrix. This matrix has for each column, okay, it has the word vectors. Okay, so this is a word that starts with an A, this is the word that starts with Z. Okay, so very large matrix, but these are the word representations. I input the one-hot encoding here, multiply with this matrix. I get the word representation, maybe 200 dimensional vector. Okay, I multiply that vector with this WE, then I multiply my previous internal state with WH, and I add my bias, and I get my new internal state. So if you look at this one comes from the input word, this one comes from the previous state, this is my bias, and now I have my new internal state. H0 is, of course, is the initial hidden state. Okay, so at the end I get a distribution like that. Okay, that gives me assigns probabilities to each of the words in my sequence. Okay, good. By the way, I mean, how many dimensions are there in this vector? How many elements are there?
Which vector?
This one.
The number of the words?
The number of the words, so it's very large, it's like 40,000 dimensional, right? Sometimes we don't like it, okay? Instead of doing that, maybe I can output a 200 dimensional vector, and that vector is going to be my vector representation of the vector I am outputting, right? So that 200 dimensional real vector doesn't have to correspond to any of my representation, but the closest one is the one maybe I choose. So that can happen too. Okay, so different possibilities are there, and people have tried those. So far it seems nice. But still, as always, okay, we have problems like this one. Recurrent computation is slow. Why do we say that? Because in order to able to calculate the output of this node, I have to start, okay, get the output of this one and feed it to here and feed it to there and feed it there. So there is a sequential thing going on. So recurrent computation is slow. That's one thing. One of the disadvantages. Unfortunately, we can't do anything about that because this is called recurrent neural network. Okay, you have to start from the beginning. That's one thing. We won't be able to solve that problem. The other one is, I think that this one is kind of maybe it will come to your surprise, but this one says that I can remember things that happened way before me, like 40 words before me, but it turns out that this architecture is not good enough to remember words like 10, 15 words before me. Okay, in practice, difficult to access information from many steps back because of the problems with the gradient descent approach. Okay, because of the problems with the gradient descent approach, and we are going to see it. We are going to look at this problem, two problems, vanishing gradient problem and the exploding gradients problem, and in a few minutes. Okay, I'm going to skip this one. No, maybe I'm going to look at this one. So how do we train this? We train it this way. Okay, training is very easy. When I give this the word, okay, I expect you to get students out of it. When I give students, I expect it to get opened. When I give the opened word, I expect it to get there. When I give there as an input, I expect to get exams. So every time I input a word, I get a word out, and if those words are different, the outputted word and the expected words are different, they are adding to the loss, right? They are making the loss even worse. Okay, so I am forcing these weights so that all of these words are the words that I am expecting. Okay, so that's how you do the training of the RNN. That's how you do the training of the RNN. Okay, like the opened, and then there, and their exams, and if you put them together, all those losses, okay, you get one large loss, and you take the derivative of this loss with respect to WH and WE. But I need to take the derivative of this loss over here, WH and WE, WH and WE. So I need to take the derivative of this loss with respect to WH and WH and WH and WH. Every time the values of WH are changing, kind of a very different case, keep taking the derivative of the same weights over and over again. So it's like taking the derivative of JWH times derivative of JWH minus 1. So it goes all the way back to the beginning. If I am going like 20 steps back, words back, I have to multiply these one by one all the way to the beginning of the sentence. But these are derivatives, right? These are slopes. Usually these are very small numbers. Okay? If you keep multiplying these numbers together, if you multiply small number with a small number, a number small less than 1, it becomes very close to 0. Okay? It becomes very close to 0. Well, in that case, my gradient descent will not work much. So it will converge to some place, but that place is not going to be my optimal position. Well, I wouldn't call it converging. Maybe it gets so slow to move, and that wouldn't give me any results back. So that's why I say that. That's why I say that here. Okay, difficult to access information from many steps back. Okay, like 20 words or 40 words back, I cannot access that information. That's the disadvantage again. That's the disadvantage of this method. This method is nice because I don't have the window problem anymore, but because of the stochastic gradient descent, I cannot train this RNN so that I get information like 40 words before me, unfortunately. Okay, that problem still exists for RNN systems. Okay, so
Do we usually use this sentence base, or let's say we have a large corpus, a dump of Wikipedia. Do we start from beginning to the end of the corpus without resetting H vector, or do we reset it to 0 in all sentences?
well, usually you cannot go more than 10 words before you. Okay, if your sentence is longer than 10 words, you will have to cut your sentence into more than one part and feed only during the training, of course. During the training, feed only 10 words before you. During runtime, there are no limitations. During runtime, start from the beginning and continue. But during training time, unfortunately, you cannot go more than 10 words. That's going to vanish your gradient. That's going to be problematic for stochastic gradient descent. Okay, but we'll have a solution for that one. Okay, good. Back propagation for RNNs. I think I'm going to. By the way, yeah, let's look at this one. Multivariable chain rule. Okay, if I have a function of two functions, and if I take the derivative of d dt with respect to derivative of f with respect to t, I have to do this, right? So I have one input, this one depends on t, this one depends on t, and this one depends on both of them. This would put the output. In our case, we are kind of doing the same thing too, okay? I have WH, okay? And all of these different versions of WH depends on this one, and my loss depends on it. So maybe I can write my loss this way, okay? So it is the addition of them, WJT over, okay, the derivative of JT with respect to WH, okay, for ith version. Okay, so I am going to calculate that one. So it turns out that while I am training this one, I am training very deep network, like 10 layers, 15 layers, 20 layers. Okay, back propagation through time is doing that. 10 layers, 20 layers, whatever. And if you go that many times using the back propagation, multiplying all those derivatives one by one is going to make your derivative at the end is very, very small, and that's going to make your progress a lot slower, and that will be a limiting factor for the RNNs. Okay.
We had the same problem with Markov chain. As I remember, we solved this problem by taking logarithms of the probabilities. Why?
Yeah, well, that's a very good analogy. Yeah, why don't we use the same idea of in the Markov chains we did this. While optimizing something, we used to multiply lots of small numbers, and at the end we had the underflow problem. And we converted it why don't we optimize the logarithm of the multiplication? That was the thing, but that was an optimization problem. In this case, I have to multiply all those gradients, right? What is when you say derivative of f with respect to x is derivative of f with respect to y, and derivative of y with respect to x, and if f is a function of y and y is a function of x, okay? This is our problem. This is mathematically defined as multiplication, not addition. This is not an optimization problem here. I mean, I can't do anything about that, about calculus. That's the formula. I cannot convert it to addition. If I did that, yeah, that would have been much better. But still, I mean, the problem here is, other than the numbers are getting very close to zero, okay, the problem is our gradient. I mean, remember this one, theta minus alpha times gradient of f, right? This number becomes so small, okay, that I change my theta only very small amount every step. So this doesn't move. My optimization becomes too long. This just stays at whatever its position is. Okay. So the problem in your case, well, this is going to be like a small number plus small number plus small number. Again, it's not going to be as small as 0, but it's going to be still small. Okay. vanishing gradient problem. By the way, we can use the RNNs to generate text again. This time again, grammatically it is okay, grammatically it is fine, but meaning-wise it is better than whatever that Ngrams offers us. For example, there's an Obama speech, generated Obama speech. Of course, they have trained this network on the Obama speeches. So the United States will step up to the cost of any challenges from American people that will share the fact that we created the problem. They were attacked, and so, well, that doesn't make any sense, but at least it reads much better than the previous one. So this is trained on Harry Potter. This is trained on recipes, food recipes. And this one is trained on, this one is interesting really. They have trained this on color names. I mean, if you look at a color catalog from a paint shop, right? So these are the kind of colors that they use, right? I mean, color names. This is ghastly pink. Great bat. Sand dan. Just made of stuff. I mean, usually they make this kind of stuff. So these are the RGB values of those colors. And these are all randomly generated by this network. It's making up new names for these colors, and they kind of associate these kind of names with the colors. I mean, kind of works. I don't know. Okay, so how do we know that we are doing it? You remember the perplexity? Perplexity is the inverse probability of corpus according to the language model. So what is the probability of me producing this sentence over this? So we want our perplexity lower for the whole set. Okay, lower perplexity better because 1 over p. Okay, and these are some of the results. In 2013, the best performing language model is 5 gram. Okay, 5 grams, that's the Google data set. Okay, it is interpolated, perplexity is 67%. Then in 2013-14, we started using RNNs, but not pure RNNs. Hybrid RNNs that uses 9 grams. Well, 9 grams is not possible actually for the whole dictionary. Why? Because it's too big. But for some words or for some phrases, very common phrases, 9 grams are possible. So this is a 9 gram language model for a limited set of words. For the rest of them, we use an RNN of 1024 nodes. Okay, so it is dropped down to 51. If 2 years later, still RNNs are not doing as good as the Ngrams, but then they came up with this extension of RNN. It's called LSTM. We are going to look at it. The numbers dropped down to 43 now. Okay, we are talking about perplexity of 39 or 30 here. I mean, comparing this number with this number, this 30. Okay, as obviously neural language models are doing much better than Ngrams nowadays. Okay, Ngrams nowadays. And there was a very nice slide somewhere here. I think we are going to talk about it in a few minutes. Language modeling is important, okay, because we use, I mean, predictive typing. When you do this, when you say, what happened here? No, what is this 5 epoch? Something wrong? No, it is 5 epochs. This is 5. These are not epochs.
In standard English, the comma is not the decimal.
Well, in my English, these are not. I know this because Going through one epoch takes some time, and these are decimal places. It's not doing anything. I think it started over again. I don't know. So this is hopeless. Let's stop this. So when I come here, when I say what, okay. So these are the most common questions. I think it is maybe the ones that I have used before. Can I do it with the,
Incognito.
yeah, which one is that? Can I, yeah, okay,
Control-Shift.
this one, yeah. What is, oh, it is doing the same thing.
No.
What is your name, ne demek? What is this, ne demek? I think this one and this one, did I ask these questions? I don't remember really. Bugün, yeah. Hava durumu, hava nasıl, hava yağmurlu mu? So these are all language model stuff. Bugün, ekonomi. Okay, didn't have any suggestions. When I say ekonomi haberleri, ekonomik değeri olan kayaçlara ne denir? What? Oh, kayaç is kind of a rock formation. Okay. So these are really valuable and widely used. One example of this language model for speech recognition. I mean, I heard some sound. Did you mean this or that? Okay. Handwriting recognition, etc. Summarization, machine translation, language modeling is important. Okay. Recurrent neural network doesn't meet language model. Okay. Just one way of building a language model, and we call that neural language models. And nowadays, as I said before, neural language models are performing better than the other ones. By the way, RNNs could be used for other natural language processing, like this one. Remember our part of speech taggers? Okay. So for each one, instead of producing the next word, I produce the part of speech tag. Determiner, adjective, noun, verb, indeterminer, noun. Okay. So this one works much better than what we have. Remember, we use the hidden Markov model for this one. Okay. These are our latent variables. These are the observations with the Markov models. This one works much better because with the hidden Markov model, it was a Markov model of order 1. Okay, it only considered the word before it and this current word. Okay, this one considers the words way before it, like 5, 6, 7, 8, 10 words before it. This works much better than our original Markov model based one. What else? Of course, we can do sentence encoding. Okay. Overall, I enjoyed the movie a lot. Is it a positive sentence, negative sentence? How do we do that? I can get the vector from the last one, or I could do, okay, get a vote from each of them and combine them in a new network, or just combine them together. We can do that too. And sometimes we do this kind of RNNs, okay? So question answering, okay? What nationality was Beethoven? Okay. So I get this sentence, I encode it, I get a new vector, okay? And I get a new vector out of all the paragraphs in my database, and I place these two vectors in a new network to give me this answer German.
Can they give relational data?
What's that?
Relational data. Like in I remember at the very beginning, word to vec we were given, for example, the relation between man to woman is like king to.
Yeah.
So here, for example, nationality to person is Beethoven to what?
If you train it that way, yeah, but we can already achieve that using the word vectors, right? I mean, what are you gonna gain other than that? We can already do that using the word vectors. Okay, so again, see the question you asked, what is the initial thing? So as an initial internal state, if I give the audio, okay, and I say just start producing the recognized words. So this one says for the start it is what. If I give what, if I give the, then whether. This network RNN is conditioned on this input. Input could be a picture, input could be a audio, input could be some other text, some other data set, I don't know. Or summarization, okay. So, now I talked about this basic RNNs. I am going to look at more complicated or capable RNNs, LSTMs, okay. This picture is nice. So, this is vanilla sade dondurma. What do we call sade dondurma in Turkish? Sade dondurma, sade. Vanilyalı. So, okay, this is vanilla simple RNN. So we are going to look at this different flavors of it, GRU RNN and other LSTM RNN. Then we will have multi-layer RNNs. Okay, so that's good. So let's take 10 minutes of break. We will be here around 15:35. So everybody sign this?
No.
Hocam. Ben şeyi konuşacaktım ama
Söylemedin ki.
ben de unuttum.
Ben yazdım oraya, tamam.
Ha, sen aldın.
yer var mı?
Var var. Yani soruyorlar genelde. Şeydir. İşte sınavlara çalışmıyor mu ki diyor. Sadece derste öğreniyor. O kadar.
Allah Allah.
Öyle bir huyu varmış. Derste öğreniyor.
Başlarız.
Derste öğrendiğinde mi geriye bir şey kalmıyor.
Ya ben yaşını öğrendim de o şok oldum.
67 doğumluyum sanırım.
Baya şey ya.
Genç mi?
Baya yaşlı.
Yani şeyine yaşına göre genç mi diyorsun? Aynen genç. Dinamik yani. Öyle lazım. Ya ben zaten ben genelde öyle şey yapmaları seviyorum. Mesela Erhan'ı da seviyorum. Çünkü o da mesela konuştuğu zaman şey yapıyor ya böyle
Heyecanlı.
her konuştuğu zaman bir şey katıyor sana. Onlara bir şey öğreniyorsun. O adam da öyle. Mesela ben onu takip ederken mesela normalde siyaset boş gelir. Yani dinlersin saçma sapan boş. Ya oğlum dinleye çok şey öğreniyorum. Ciddiyim bak. Dolu konuşuyor yani. Tabii etrafındakiler boş soru sorunca boş sorular soruyor. Saçma sapan.
Şeyde yani.
Geçmişi var. Yani düzgün bir adam çünkü şöyle 13 yıl bu görev o tarz böyle yüksek böyle bakanlık, başkanlık, başbakanlık bu da mesela bulunup da elinin altında her şey var yani bulunup da mesela bir hata yapmanı bile orayan güce sahip olup da o gücü kötüye kullanan çok insan var. Yani güç testini geçirmemiş, o geçmiş.
Şirketlerden başladım.
Ya mesela şey gibi bir konuşmasını. Diyor benim bir akraba çevrem var diyordu. Bakan diye benden iş falan istiyorlardı. Ben de yapmadığım için bana bize küstüyor. Tek bir şey mi dahi? Akrabam dahi öyle torpil yapmaz öyle bir şey mi?
Okay, so next week we are going to do the paper presentations. But before the paper presentations, I have some lectures to do. So how many people are going to do the paper presentations? One, two. All the graduate students actually. Any people from the online audience? Two people from the online audience too. So a total of 4 people maybe. Maybe 2 people. Okay. So I am going to give you 10 minutes or 15 minutes for each presentation. So I will do the lecture for an hour maybe, and you are going to do the paper presentation afterwards, okay? So how many lectures did I miss? I had missed 1 or 2.
No. One lecture.
Okay, so I missed 1 lecture, so we were going to do the presentations in the last this hour maybe. So next week our paper presentations from the graduate students. So you are going to do your presentation here. Okay, please come to the class. No presentations from home. I guess that will be it. Good.
Should the presentation in English?
Yeah, but this course is in English. I am not talking in English because I liked it. They make me, okay? Good. Let's move on. Let me start talking about fancy RNNs, that is, okay, LSTMs and GRUs. Okay. So this vanishing gradient problem is an important one because it kind of renders RNNs useless for many crucial cases. Okay, so we need to find a solution for this one, and we are going to look at it. Basically, our solutions will be LSTM and GRU, and then on top of it, we are going to talk about this bidirectional RNNs or LSTMs and multi-layer RNNs. Those are important stuff. So variation gradient problem. Remember, we need to take the gradient of this total loss with respect to W. Okay, those are the unknowns. But every time we take a gradient of it, as I said before, okay, gradient of the loss with respect to H. Question? You guys have a question? Yeah. Okay. While I'm at it, let me take a attendance. Okay, so with respect to H1, but with respect to H1 means that I have other stuff, so I am going to do this. I am going to take the gradient of H2 with respect to A1 times gradient of this loss with respect to H2, etc. With the chain rule, I keep multiplying many gradients over and over again. So what happens if these are small? Usually they are small. When these are small, the gradient signal gets smaller and smaller as it back propagates further. So the longer the sentence, longer the window, the worse the case. So we need to find a solution for that one. Okay. So the solution is okay. Solution is propagating a different kind of information between the time steps, and that's going to be cell state instead of internal state. That's going to be cell state, and we are going to look at it in a few minutes. And remember this one. Sometimes we need to go all the way back to the beginning of the paragraph. Okay, so long-term dependencies are important. Okay, and since RNNs are not that good with the long-term dependencies, these kind of problems keep happening over and over again. The writer of the books, RNNs usually prefer R. Okay, after the box, RNNs usually say that more than is, R is more possible because it sees its books, right? But the correct word is, of course, is. The writer of the books is, right? So this is the correct one, but that's the preference of the RNNs. And these kind of behaviors of the RNNs are observed a lot because RNNs, because of this gradient flow problem, they cannot be trained very well for the dependencies that are far away from the current word. Okay, so those are important. Remember this one. Okay, this learning rate and gradient. Okay, the standard stochastic gradient ascent steps becomes too weak to reach to the previous word, way before previous words. Okay, that's one thing. The other thing is that just the opposite side of it, exploding gradients. Sometimes gradients are so large. Remember what happened when I chose the learning rate very large? Okay, when I chose it, just oscillated. It just behaves like crazy. It just goes one way and then goes back the other way and goes. So I did that by choosing this learning rate large. What happens if the gradient is large? That would have the same effect. Okay, sometimes I would have numerical degeneracy cases like the infinity and those kind of numbers. Okay, so that's called the exploding gradient problem. This is an easy problem to deal with actually. Okay, what you do is, if the gradient is too high, if the gradient is larger than some threshold, then I just normalize it. Threshold over the length of that vector, and I have this one. So I am just I'm just scaling back that gradient vector to some proportion to it, smaller proportion of it. Okay, so this is a easier problem than the vanishing gradient problem. And this is just, okay, this is called gradient clipping. Gradient clipping. You just, okay, if this is my gradient, very, very long gradient vector, I just take it smaller along the same direction and continue. And this is one example. If the gradient is too, say the gradient is very large here because there is a sudden drop, and if I take this gradient, I will be way off. But if I do the clipping, I can find that minimal point in that position. So I'm not going to talk much about it, but gradient exploding gradient is just the opposite of the vanishing gradient. So we solve this problem. Let's look at the problem of, okay, how to solve this problem of vanishing gradients. So you remember this, right? Let's remember, this is our bias, this is our current word, this is the matrix that I multiply the current word, this is the matrix that I multiply my internal state. Okay, so the thing is this, I am going to add more memory for the RNN to remember things from way before. Okay, I am going to do this, an RNN with separate memory for remembering things that happened way before, and that model is called long short-term memory. And people always think that is a development after the deep learning stuff. No, it was invented in 1997, and this was way before people have invented neural language models. Okay, and I think this is biologically motivated too. Okay, on step T there is a hidden state HT, and there is a cell state. This cell state, okay, is not affected by these gradients, and it carries information from the previous states. Okay, our output, our input, and our previous state are connected to this hidden state. Similar stuff happens with the cell state, but this is kind of special, and you are going to see how we treat this one. Okay, both are vectors length n. Okay, if I have 100 nodes for the hidden state, I will have the 100 nodes for separate 100 nodes for the cell state. Okay, and the cell stores long-term information. And this LSTM, long short-term memory, which is a specialization of RNNs, can erase, write, and read information from the cell. Okay, say that. Okay, you remember stuff from the previous verse, previous time steps. Okay, depending on what happened in my current input, depending on my current internal state, I can erase stuff from my cell state. I can add more stuff, or I can just read it to make some reasoning, make some induction from the current state. Okay, so the selection of which information is erased, written, read is controlled by the three corresponding gates. These are called gates. Okay, these gates are either open or closed, or somewhere in between. So typically we use sigmoid function as the gates, because sigmoid function produces numbers between 0 and 1. We like that. Okay, and they are of course dynamic, and their values are calculated using the neural networks again. Okay, well, this might look a little bit complicated, but it is not actually. Let's read it. You remember this, right? Okay, this is the forget gate. Let's read this one. Okay, bias for the forget gate. Multiply the current input with the forget matrix. Multiply the previous hidden state with the forget numbers, and this sigmoid is going to give me a number between 1 and 0. So this is going to tell me what kind of things I should forget from my internal state. Control what is kept versus what is forgotten from the previous state. Okay? So these are the sigmoid functions. The same thing as again input gate. What kind of things should I put into my system? Okay, these are the input gate. An output gate controls what kind of things should I output. Okay, and this guy calculates my new cell content. Okay, my cell, whatever I am remembering from the previous states, previous occurrences of the neural network. Okay, again, I mean these are all parallel, right? I'm just changing their names again. Bias U and W, bias U and W. So for each of them. The only thing is that these two are different. Okay, this is the cell state. Okay, this is the hidden state. So these circles, okay, these are not dot products of vectors. These are element-wise products of vectors. Okay, element-wise products of vectors. So if this is my vector a1, a2, a3, and this is my vector b1, b2, b3, this operator gives me a1 times b1, a2 times b2, a3 times b3. So this is a element-wise product operator. It is not dot product. Okay. So this one says that. What does it say? Just read it. Get your previous cell state. Forget whatever you are forgetting. Okay. Get your new content. Input whatever you are inputting. That will be your new cell state. And this one says that. Get your cell state. Take the hyperbolic tangent of it. The hyperbolic tangent is something between -1 to +1, right? So it can change your internal state in a way that sometimes your positives will become negative, sometimes whatever you have will be erased because it can include zeros, and depending your output gate, your hidden state will be like that. Okay, so it might look like some very ordered, some very random decisions, but it turns out that this works very well for most of the cases, and usually we do that kind of stuff. Okay, these are our inputs, these are our outputs. This is my, okay, this line is my cell state, this line is for my internal state, and you see this one, this is the forget gate, input gate, output gate. Okay, this one sigmoid produces things between 0 and 1, right? This sigma produces things between 0 and 1, and those are all multiplied with the cell state. So 0 means that forget about that, 1 means that keep it, just keep remembering it. Okay, this one is for output again, so this one is related to what you should output. This one is not related to what you should output. This one is what you should learn from your input. Okay, so that's what's going to be, and remember this one is getting my internal state too, internal state from the previous one.
Can I ask, when two lines get together, what does that
That's
mean?
the concatenation of two vectors. If I have a 100-dimensional vector, another 100-dimensional, now I have 200-dimensional vector.
Okay, so below is the C
What?
vector, and above is the h vector, right?
Well, yeah, this is a vector, and this is a vector of dimension of
There are two. There's I think the c vector and the h vector.
Where is C vector? Oh, yeah, C vector is here, H vector is, this is C, this is H. Okay. Good. So this means concatenation, this means copy. The same copy is sent there and sent to output too. And this is our internal state. So as you see, this internal state is only pointwise multiplied, okay, and is added pointwise added, like that, and it goes like that, and you don't see any parameters playing on it, so it can go as far as back, okay, back to the beginning of the sentence. But if I look to if I like to run the loss function, I have to do this. I have to do this. So I have to go through my parameters, then I have to take the derivative with respect to those parameters here. Okay? Derivative with respect to those parameters. That's the nice invention about it. That's the nice idea about this LSTM stuff. Oh, okay. So your question. This is concatenate. So this is copy. The vector transfer. Pointwise operation. Neural network layer. Okay. So everybody uses this stuff. This guy is nicely giving credit to whatever he's getting the slides from. I'm not that nice. I just use them. But again, this is the Manning is the guy where I took my slides, and he has nice videos on the YouTube too. His lectures, just watch it. So he tells about this much better than myself. Okay, so these are the things maybe. Okay, write some new cell content, forget some content. Okay, this one forgets, this is just input. Okay, this is forget input gate, compute input gate, compute. Okay, question for you, why this is a sigmoid but this is a hyperbolic tangent? Why didn't they use sigmoid here too? Why sigma, sigma, sigma, and hyperbolic tangent? Sigmoid, sigmoid, sigmoid, and tangent H.
Don't both of them give values between -1 and 1?
Yes.
Yeah, because you are learning new stuff, right? These are either keeping it, okay? These are either keeping it or outputting it. This one says that I am going to put more stuff in. So
Maybe
0 is a possibility, just don't put anything. +1, put it in a positive way. -1, just subtract it from your cell. Okay. So that's the long short-term memory kind of stuff. Okay. So if you do that, our vanishing gradient problem is mostly addressed. We are not saying that it is gone. Okay, we are saying that it behaves much better, LSTM architecture. So for our network, for our RNN to keep information over many time steps, for the vanilla RNN, it is more difficult. Okay, and we are not saying that we solve the vanishing gradient problem. Doesn't guarantee that there is no vanishing exploding gradient, but it is a much better behaving system in terms of those two problems. Okay, and these are some statistics. Okay, in 2020, when you go back and look at these statistics, okay, a workshop on machine translation in 2016, okay, when people started using the neural language models, okay, only 44 people talked about RNNs. When 2018, okay, RNNs are 9 times and transformer is 63 times. Nowadays everything is transformer. Okay, so LSTM is kind of becoming dead. Now we will talk about transformer more and more.
So,
Transformer says that, okay, remember one of the problems with RNN, let me go to RNN approach. Where is my RNN? Lectures, okay, let me open this up. This one, the problems of RNN, let me find it. Two problems we said. One is the gradient, vanishing gradient problem, and the other one is the slow execution time, both training and testing time. Couldn't find it. Is that problems with the RNN? Yeah, well, the second one is again the second one is, I couldn't find it, those two sentences, but second one is, it is slow because you have to start from the beginning of the sentence, and both training and testing it slow. This transformer stuff that I just talked about addresses that slow problem. Okay.
LSTM or standard RNN is slow. Both.
LSTM and both of them are slow, yeah. And because they are sequential, right? The window length of 1 and window length of 1, you have to start from the beginning and you have to keep giving these over and over and over again. I cannot parallelize it, right? I cannot give many training instances at the same time, so I can't use the GPUs, and I said it becomes a problem. So transformer kind of goes back to the fixed length window stuff. Okay, transformer is kind of doing that. You give fixed length input to the transformer and it learns that much of it, but you train it with so many examples of it and it becomes much better than LSTM. And later, and we are going to talk about this, the basic building block of transformers are the attention mechanism, and we are going to look at the attention mechanism next week, I guess. Okay, and nowadays everything is about transformers. There are visual transformer networks that works with the images. There are video transformer networks that work with the videos. For the speech, for the other sequential stuff, so the transformer stuff is working very well. So people used to say that, okay, LSTMs are the solution to this kind of problem. Now we don't like LSTMs anymore. Maybe you heard about it. Convolutions are solutions to everything, but nowadays we say that we don't like convolutions anymore. The new kid in block is a transformer, and it is performing better than the other alternatives. And for the transformer, doesn't matter what kind of data you are working on, whether it's a word or image or video or speech or whatever. Okay, so everything is the same for the transformer. Okay, so an alternative for the LSTM is GRU, gated recurring units. This one was invented later after LSTM, of course. So you say that you don't have to be that complicated for this kind of an effect of vanishing gradients. All you need is just a update gate and a reset gate. Okay, so the number of gates is less. In fact, instead of 3 gates, I have 2 gates, and that solves many of the problems. And And usually, when we start working on a problem, okay, this guy says start with an LSTM, but usually we start with the GRU. Okay, GRU is simple for speed and fever parameters. It trains very well. If GRU works and gives you the desired performance, keep using it. Otherwise, you may need to switch to LSTM. If you don't have enough number of samples, your data set is small, then GRU is the way to go. So it is simplified version of the LSTM. That's what I said. Another solution for this vanishing gradient problem is, okay, vanishing gradient problem is not invented by the NLP people. Okay, if I have a network, like this is my input. Let's say this is my picture. I gave this picture to this. Okay, 20 layered with a network of 20 layers, and this one says that this is a picture of horse or a car. Okay, so there is a 20 layers. So the vanishing gradient problem, backpropagation, exists in this kind of network too. Okay, so to solve this problem in that case, they invented these kind of network structures. They build these kind of skip connections between the layers, so the gradient flow is free on this skip connection. Okay, so this works very well. Before this kind of structure, the deepest network was like maybe 30 layers. After this kind of structure, they were able to build deep networks of depth 100, 150, sometimes 1,000 if you like. Okay, if you have enough data, you can train them, and these are called residual networks because it is working on this residual value here. So ResNet or residual networks. Another one is the dense network. Okay, this one says that why are you doing the skip connection between these kind of nodes? Why don't we connect everything with everything? Okay, skip connection. Then it's called DenseNet, and this one works a little bit better than the ResNet. Okay. One variation of RNNs or LSTMs is the bidirectional RNNs. Okay. So remember what we do. We give and the output goes to here, movie goes there. So the movie was terribly exciting. If I only read 1, 2, 3, 4 words, I would say the movie was terrible. Like the movie was bad. But the whole sentence is the movie was terribly exciting. Okay, so it's a positive sentence actually. Okay, since I started reading the sentence from the beginning, and I have only read 4 words without paying attention to exciting, at this place, at this time, my RNN or LSTM is going to say that this is negative. But if I started from the other side like that, okay, I wouldn't have this problem. So the idea is left to right or right to left, both of them are missing crucial information about the whole context. Why don't we put them together? Okay, why don't we put them together like this? One network reads the words from left to right, the other one reads the network from right to left, and then my output nodes, the outputs of the nodes are concatenated together like that, and each one can make a decision by looking at the whole sentence now. Okay, it is not just up to the point where from the beginning of the sentence. So these are called bidirectional RNNs. Of course, for these kind of RNNs or LSTMs for work, you need the whole sentence in your hand. Okay, this doesn't work online. I mean, RNNs has this nice property of whatever you have, I am going to work. This one says that give me the whole sentence because I am going to run two RNNs from left to right, right to left. These are called bidirectional RNNs or bidirectional LSTMs. Okay, that's one variation of it. Good. Another one is, okay, another one is multi-layer RNNs. So far the network that I showed you about RNNs are just a single layer, but this kind of RNNs are possible too. Okay, the output of each of these are fed to another layer of RNN, and the outputs are fed to another layer of RNN. So this is an RNN of depth 3. Okay, remember what I said? People who are doing the computer vision, they design networks of depth 100 or 150. In NLP world, we don't use that kind of deep networks. Our networks are only as deep as maybe 4 or 5 layers at most, but our length, like that one, could go as far as the number of words in our text. But this kind of depth is maybe 2 or 3, and this is possible with multi-layer RNNs or LSTMs. Okay, many libraries, deep learning libraries, support this kind of structure. Okay. Okay, so high performing RNNs are often multi-layer. Okay, so somebody found this. For neural machine translation, 2 to 4 layers is best for the encoder. 4 layers is best for the decoder. So we are talking about at most 4 layers LSTM stuff. If we are using transformer stuff, which I'm going to talk about next week, okay, then 12 to 24 layers. But these are kind of special layers. They are repetition of the same thing. Is optimal. That's what we found. Okay, so that will be it for the special RNNs that will take care of the vanishing gradient problem or the exploding gradient problem. We talk about it, and we talk about the bidirectional stuff, and we talk about the multi-layer RNN stuff. I guess that will be it for this one. Next week, as I said, we will talk about those transformers, and we will talk about maybe this machine translation stuff. At the beginning, it all started with machine translation. Actually, this artificial intelligence, area of artificial intelligence. Okay, so as soon as they realized that the computers could be used for this kind of stuff, one of the early tasks they looked at is to play chess. Let's play chess, because if I can play chess, that means that I am intelligent. The other thing is that if I can translate between 2 languages, that means that I am intelligent. Okay, so playing chess failed miserably. They couldn't do it. I mean, it didn't play very well because they didn't have the memory, they didn't have the CPU power. How about translation from Russian to English? Because they had to translate lots of technical documents from Russian to English. They thought that in 1950s, Russians are making lots of progress technically, so they are sending satellites to the space. They are sending people to the space, and USA is not doing anything. So let's get lots of books from them, and let's translate them automatically. And who's going to translate it? Computers are going to do it. So this was the approach. The approach is, let's just translate the words one by one. Let's handle the grammar, and it's going to be okay. So for 60 years, from 1950 to 2010, they worked on this idea for 60 years. It didn't work. And after 2010, this neural machine translation came in. Nowadays, it is working very, very well. Neural machine translation. Okay, so we are going to look at it next week, and for that one, we are going to use we are going to use again our LSTM stuff. Let me show you that one and let me stop at that point with the neural machine translation. Yeah, okay. So you give this French sentence. Okay, I don't know how to read it. I just decode it. This is called the decoder. Okay, encoder RNN. I give this sentence one by one. After that, I say, okay, start producing now. It produces the English sentence. As you see, I don't talk about the word correspondences. I don't talk about the grammar. I don't talk about the morphology. It figured everything by itself. And this works much better than the techniques that we have spent 60 years on. Okay, nowadays everybody is using this one, including the Google Translate or the other kind of translation tools. Good. Any questions? Okay then. Next week I will do the lecture on this a little bit. Then we will talk about our friends are talking about the paper that they studied. Okay. See you next week. Same time here.
Dear, I want to ask you a question.
Sure.
Mandatory from university presentation next week?
Yes, that's what I said last time. 1 hour ago, you will be here. All the presentations will be done in class.